Hello, good afternoon, everybody. Thank you for joining us again. Today we're going to discuss the debug architecture that's on the Cortex-M microcontroller family. This is a proprietary architecture called CoreSight, which is developed by ARM. And along with giving you the standard sort of run and stop type debugging, it also incorporates a number of trace units so that within our real-time system, we can do a lot of on-the-fly debugging and see how our system is performing. It also has some interesting features that help system verification as well. So we'll have a look at those and how we can do some software testing on these devices as well. So we have our Cortex-M microcontroller, and internally it has the CoreSight debug architecture. Now this is completely independent of the Cortex processor, so it has its own bus system and doesn't rely on the processor to carry out any debug features. So the earlier JTAG was just really a way of inserting instructions into the processor so we could build up debug features. So CoreSight's completely independent. It can debug in and out of low power, which is another nice feature as well. So we can put the Cortex processor to sleep, but the debug architecture keeps working. And also, depending on the silicon vendor, we can decide what happens to some of the peripherals when we stop the processor. So we can freeze things like timers and some communication peripherals while we're single stepping. So any interrupts stay in sync with our background code. So inside the Cortex processor, we have the debug system. So this contains basic run control features, so we can single step, set breakpoints. We can look inside the memory and peripherals. Now on the larger Cortex microcontrollers, so the M3, M4 and M7, we have the option of a number of trace units as well. So these trace units are an optional fit, but two that are normally fitted are the data watch trace and the instrumentation trace. So the data watch trace can flow out data about the internal memory areas in real time, and the instrumentation trace basically acts a bit like a serial port, so it connects you up to a console window within the debugger. So this allows you to put printf style debugging inside your code, and as the code's running, you can send yourself messages onto the console window. So this is very good for flagging runtime errors, but it's also, as we'll see later, an excellent way to do software testing. Again, on the larger Cortex microcontrollers, there's an additional optional debug trace unit. This is called the ETM, the Embedded Trace Macrocell. And this can flow out every instruction that's executed. So we can get a real-time instruction trace of the assembly code and reconstruct that into C code. And again, this is an optional fit, so very often it's only on the more complex higher end processors. But if you want to get instruction trace, you need to have a device with the ETM fitted. One point to be clear of here, on the smaller devices, the M0, M0 Plus, we don't have the data watch trace, so we don't get this stream of real-time information. However, the debugger can access the internal memory on the fly. So while the processor's running, the debugger can peek and poke into the internal memory of the processor. So while we're not getting a stream of values coming out, we've still got access to the internal memory while the code is executing. Now, in terms of connecting to the processor, the minimal connection is 2 wires. So this gives us the serial wire debug. So this will give us basic run control and the ability to read and write to the internal memory. And normally these pins will automatically be debug pins on the processor, so we can just connect our debugger and take control of the processor. There is then a third pin called the serial wire out pin. So this is where the instrumentation and the data watch trace are connected to. And you need to have this pin if you're going to receive data from these units. This may be a dedicated pin, or it may be multiplexed with a GPIO or other peripheral. So in order to get the serial wire out, we may have to do some further configuration to the processor. And this is in the form of a small script file, which will convert this pin to be the serial wire out pin from its standard setting of a GPIO pin. But this is a bit dependent on the silicon vendor, so it will vary from device to device. We have a similar situation where we have the embedded trace macrocell. This takes an additional 4 pins, but these will almost certainly be multiplexed with GPIO. So we need an additional script file to convert these from GPIO to be the trace pipe. And sorry, the one thing I should mention here as well, when we connect to these devices through the serial wire debug, there are actually 2 types of connection protocol that are supported. The first one is called a UART mode, and this is generally used by the lower cost tools. So that will allow a connection of up to about 10 megabits. There is a more advanced mode, a Manchester encoded mode, which will then run up to 100 megabits. So both of those sound quite fast, but when we start using the data trace, the instrumentation trace, we need really as much bandwidth as we can off of the chip to get out lots of real-time information. So this, for the lower cost tools and the CMSIS DAP type tools, this then does become a bit of a bottleneck. So when we are configuring our device, we have in our debug setup, when we install the CMSIS pack for our device, it will put on the scripts necessary for our device. So here in the debugger, we have a pack tab. We then have the debug script for this particular microcontroller. So when we launch the debugger, this script will execute. And then this script is one of these little templated files. So here we can tell it where the serial wire out pin is. If we've got a bootloader on the chip, we can tell it how to behave. If we have an additional processor or any other unique features, we can manage those within this script file. So in terms of just connecting the device, you'll be able to get a debug connection very easily. To get the streaming data trace and the ETM trace, you will need to configure this little configuration file. As I mentioned during the CMSIS section, we have this standard called CMSIS DAP, which is a block of firmware. This can convert a standard microcontroller into a CoreSight debugger. And this supports all of the low-level features, so serial wire debug, and it will also connect to the serial wire, the trace and the instrumentation. So you can do a good level of debugging with really what in effect a zero-cost tool. Its main disadvantage is that it's generally mounted on an evaluation board. Some of the manufacturers have designed them so that you can either break the debug section off and use it separately, or there are simple headers that you can move it onto another piece of hardware. But its main drawback, I think, is that it is a bit bandwidth limited, both between the debugger and the microcontroller, and also the USB up to the processor as well. There are a large number of commercial debug adapters that are available. There's a set from Kyle called U-Link, and these offer a range of different debug features. So the first of these that was brought out was this little U-Link 2. So this debugs using the UART mode and has a USB 2 connection to the PC. A more recent version of this is called U-Link Pro. So this gives us debug up to 50 megahertz and also connects to the device in Manchester encoded mode. So we get a very high bandwidth for the trace units. The U-Link Pro can also connect to the embedded trace macro cell, and this will then give us a streaming trace up to 800 megabits a second. So by streaming trace, there's no actual buffer inside the U-Link. We stream every instruction that's executed and we record that straight onto your hard drive. So we can amass a complete list of what's been executed on the chip. There is another version of the U-Link Pro called the U-Link Pro D. So this has the same high-speed performance, but isn't fitted with the to support the embedded trace macro cell. So it just is a higher performance debugger. And then we have a newer unit called U-Link Plus, which I'll come back and look at a bit more detail later on. So this again gives us a high-speed USB and a fast connection onto the processor. In addition, it can do power measurement, so we can analyze the power consumption of our microcontroller during runtime. And it also has a digital and analog logic analyzer, so we can generate signals onto the board and we can read signals into the debugger. So we can look at real world signals and we can generate test patterns for our target hardware if we want to as well. So again, this is a very interesting new unit. Now, historically, a lot of ARM microcontrollers supported JTAG, and we had a standard 20-pin connector for our JTAG tools. And this is, by today's standards, a honking great connector, which takes up a lot of real estate on the PCB. If you're developing your own hardware, then there are smaller sub-miniature connectors that are now defined as the standard connectors for Coresight. So there's a miniature one here, which is a 10-pin connector. And if we're using the ETM trace, we have a 20-pin connector here. So this one maps onto here. So the lower 10 pins are effectively this connector, and then the trace pipe is brought out on the upper pins. So if you are developing with a device that has the ETM fitted, we would recommend always fitting the 20-pin socket onto your board. So if you need it, you can get at the instruction trace. If your hardware engineer hasn't pinned this out, you're forever stuck using just the standard debug features. So again, you do need to talk to the hardware department, who always love to put this on, or even really like to put this one on in preference. Now, all of the debug architecture connects up to the debugger, in this case, the Microvision debugger. And this is probably one of the most highly featured debuggers for Cortex-M that's available. So we're going to have a look through what's available within the Microvision debugger, and we can use this as a guide as to the sort of debug features that you should expect from any other debugger. Okay. So this is integrated into the IDE. So we start a debug session. We have access to many of the standard features that you'd get in a modern debugger. So high-level language debug, watch windows, memory windows, peripheral view windows, and we can look down into registers, etc. here. Also, we've got a disassembly window in here. We can set breakpoints by just clicking in the margin, and we can also set data breakpoints as well. So when a variable is accessed, we can halt our code. There's a command window here, so we can generate script files and execute scripts within our debug tool. Now, in addition to those sort of standard debug features that you get on most debuggers, the Microvision debugger will also support instruction trace. So if we have an ETM on our device, we can use the U-Link Pro, connect to the trace pipe, and then we can get a C-level trace. And as I mentioned, this is a streaming trace, so we're actually capturing everything. So this is actually better than in-circuit emulators that used to cost about 10 grand and had a limited trace buffer. One issue we have found with the instruction trace is, although the U-Link Pro is spec'd to work up with processors running at a core clock frequency of 200 megahertz, we tend to find that it tops out about 140 to 160 megahertz. And this is mainly because the way that the GPIO pins have been implemented by manufacturers, they're simply not fast enough to support the instruction trace. So you need to do a bit of investigation when you're selecting a device if trace is very important to you. Okay. But once we've captured trace, we then have a number of other windows within Microvision that will give us code coverage. So as we've covered every instruction, we can work out a very accurate code coverage of our device, and we can also show performance analysis. So the run times, the number of calls, average runtime, etc., to all of our functions. And this information can also be displayed alongside the source code as well. So we can see the execution time for lines and also number of calls to a function if we want it as well. So this really gives a feel of a very powerful debugger, about the equivalent of a mid-90s in-circuit emulator for an 8051. On the M0, we have another kind of trace, which is a micro trace buffer, an MTB. So here we're taking a bit of the user RAM and we're converting that into a circular buffer. So as the processor is executing, each instruction that's executed is recorded into the trace buffer. When we halt the code, a low-cost tool can then download the contents of that buffer, and then we can rebuild the instruction trace. So this gives us a snapshot trace buffer on these very small devices. So currently this is on the M0 Plus, but it's also been added to the next generation of Cortex processors, M33, M23, M55. So this will become a standard for tracing memory devices. So it's for tracing instructions as time goes on. And this is configured by another one of these initialization files. So here we can nominate the buffer size that we want. We can say where we're going to put it in the user memory, how we want to handle the buffer, either as a circular buffer or we just want to stop. And we can also break the target as well. So we halt execution, and then we can say where the micro trace buffer debug registers for a particular manufacturer located as well. Again, this is installed, and when the debugger starts, this initialization file will be executed. So we set up the trace buffer. Now, with the standard low-cost tools, so not the ones that support the embedded trace macrocell, we also can look at a number of counters that are within the core, the M3, M4, and M7, and this will give us sort of a high-level trace of how your code is executing. So we can see exception entries and returns, data reads and writes, so we can see have a bit of an idea of the flow of the program. There are also a number of performance counters that will give us some idea of how well the code is executing on our processor. So here, the extra cycles per instruction are effectively wait states that we had trying to access the flash memory. So if you remember, we have a memory accelerator module that's trying to make that as efficient as possible. So ideally, this number should be as low as possible. So it can be used for sort of benchmarking. The same here for exception overhead cycles. So if there's a delay getting into an interrupt, we can see any overhead that we're suffering. Again, sleep cycles, load and store count cycles, and this one, folded instructions, is a bit of voodoo. It's where an instruction went through the pipeline and effectively took 0 cycles. Again, we have another exception trace, and this one is quite useful. So we can see the number of times an exception is executed, the total runtime, and then max, min, and average runtime. So this gives us a very good idea of the overhead of our interrupts on the processor. And again, this is available just with the standard tools. So when we come into the debugger, there's a number of views that we can customize, and we'll have a look through these as we go along this afternoon. So here we mentioned before that there is a system viewer description file. So this is an XML file that's generated by the silicon vendor. So that work is done once, and then it can be used by anybody that's making a CMSIS compliant debugger. This gives us a big advantage that you're not waiting for your particular tool vendor to implement the peripheral views for your particular device. If the silicon vendor has got their act together, then this will be available from day one. And here we can open up, and this gives us a view into all of the peripheral registers and the internal flags inside them. There is a similar view within the Microvision debugger called the component view. So this again is an XML file, but it allows us to look into a software library. So in this case, we're looking at the real-time operating system. So we can see all the values inside the kernel, and then our different operating system threads. So we can see how the code is executing in here. So many of the Kyle middleware components are instrumented so that we can see these views. And here we can see the stack usage, and also the maximum stack usage is available as well if we enable it. Now you can design these for yourself as well, and we'll have a look at doing that in a later webinar. So here, if you do want to have a look at that now, if you go to the pack installer, and if you select the ARM as the silicon vendor, then go to the examples, there's a number of examples of how to generate these system viewer description files or system component viewer description file. And here we can look at symbols in our own code and display those graphically. Now we've done this for a number of customer projects. So you build, it's almost like building a custom watch window. And although it takes a little while to do it, it becomes so useful as you go along. We'd certainly recommend learning how to do it. So we would create our system viewer description file, and then within the debug window, we can load that into the debugger. So when it's launched, we now have access to our own component viewer. So again, we can easily customize the debugger this way. As I mentioned, there's a second real-time unit, the instrumentation trace. So this acts like a UART, but it is in fact a packetized structure. So it's got 22 channels. So that kernel information that's sent up to the component viewer uses one channel, and then we have a public channel which we can use for our printf commands. You can use other channels to write to a file on your hard drive. So you can sort of printf test information to a file and store it. So this, for our public use, this is configured again through the runtime environment. So in this compiler section, we have an IO section, and then we can enable the standard IO channels. And here we can either select user, where we can direct it to a peripheral like a UART, or if we select ITM, we will direct it to the instrumentation trace. This adds some low-level put char, get char code, and then whenever we do a printf, it will come out in the console window that's in the debugger. And again, this is pretty straightforward to set up, and it's extremely useful. But it's only available M3, M4, and M7, not on the M0, M0 Plus. If we're using the ITM, it's a very good means of reading and writing test information down onto the microcontroller. And there is a test pack for a test framework called Unity. So this is an open source framework for C code that's been specifically developed for embedded systems. So again, we can install that as a pack from the pack installer. And then within the runtime environment, this becomes available as a test framework. So we just need to tick the box here, and then it will add our test framework here. And we can then add our production code, and then we can add calls to our test framework around it. So we'll take a look at this now, but we go into this in more detail in a later webinar. Okay. So here, we could have main, we can call the Unity test framework. We then call run all tests, and we can then set up groups of tests for different modules in our code, and we can call execute those. And then in each of our test groups, we can run groups of test cases. And then in our test cases, we have a bunch of asserts. So here we're doing the return from a function to a pre-calculated value. So we can have pass or fail on that. And there's a wide range of these asserts available. Or we could compare a variable to a global variable or a local as well. So this is quite flexible, and it's very quick and easy to generate. Okay. So here we'd be writing our C code, and then we're writing test cases to go alongside that. So Unity works as a very good, what I would call a developer test framework, so that you can write C code, write tests to go around it, and then every time you go into the debugger, you can run those tests to check that you haven't broken your code. And even if you know it works, by going through this process, you will find ways to improve your code. And again, we've used it on a number of projects, and it's been quite effective as a simple test framework. So again here, if you want to have a look at this, once you've installed the pack, if you go again to the devices, and then the ARM as a vendor, and then there's a couple of Unity examples in here, and these run within the Microvision simulator, so they're not specific to any particular bit of hardware. So you can have a play around and see how they work very straightforwardly. And that will all work within the evaluation or the light version, which you can download and try out. And the light version allows you to write up to 32K of code, and it also grants you a commercial license. So any code that you generate with it, you can embed into a commercial product. Now, as I've mentioned, the simulator, going back to about 2000, Kyle were producing full simulation models for the processor and also the microcontroller peripherals. But as the Cortex-M processor took off, the number of devices just escalated. So it was impossible to develop all the simulation models. So there are a number of legacy ones that are still in there, which are very good for training and experimenting with. But nowadays, the only new simulation models that have been added are for the processors themselves. So at the moment, we've got M0, M0 Plus, M3, M4, M7. There is a model for the M33, and that's done a slightly different way through what's called an ARM fast model, and that is available as part of the full Pro version, or you can purchase it separately. Now, the simulation cores are actually very good for testing pure C code. So if you have C functions that don't actually touch registers in the processor, you can build test harnesses to test those functions using the simulator. And that again is quite an effective way of testing your code if you don't have lots of hardware available. Now, if you have a lot of testing to do, the Unity framework, you quite quickly hit its limits. Every time you make a change to a function, you have to maintain all of your test code. You then have to spend a lot of time doing all the documentation as well. So it's good as a test framework to build confidence, but as if you have a large amount of testing for a safety certified product, you kind of will start to hit the limits of what it can do. So Microvision has a TCP socket built into it, so other third-party tools can connect and control the debugger. So another tool that we use is a tool called Tessie. This came out of the German automotive industry, and it's a very comprehensive test tool that is specifically designed for small embedded systems. So here we can analyze our C code. We can graphically set up test cases. We can do auto generation of the test harnesses. So it will generate the test harness, download onto the target, run the code, give you pass fail, and then generate all of the documentation. So the advantage here is that you're spending a lot of time concentrating on the tests, not maintaining the test code. And in one of the later versions, it now does what's called mutation testing. So it will make small changes to the actual source code. So to check that your set of tests will detect that error. Okay, so this gives you confidence that you've generated a full spanning set of test cases. And then hopefully it will changes the mutations back again. There's also software metrics. So this includes a McCabe cyclometric complexity. So this tells you the number of paths through the test code. So this is a good indication of how many tests that you need to do. So again, this bigger overview is available on our website. You can download the Tessie software from there as well, and you can get a trial license to experiment with it. But again, if you need it, it saves you an awful lot of time and money. Otherwise, it's probably a bit of overkill if you're not doing extensive testing. It's reassuringly expensive. Now, another feature in the debugger that's come in over the last few releases is a thing called the event recorder. So this works in a similar fashion to the micro trace buffer, but it's implemented in software. So what we're effectively doing is taking a bit of the user RAM and arranging that as a circular buffer. We can then instrument the code with event annotations, and when they execute, they write into the event buffer. The debugger can then read the memory buffer, and that's non-intrusive, and upload that to display all of the event annotations in the debugger. So this technology works on all of the Cortex processors, including M0 and M0+, and we can also use it as a printf style debugger as well. So here in our compiler section, we now enable the event recorder. We configure it in a similar fashion to the micro trace buffer, and then for our standard out channel, we can set that to the event recorder. So now when we do printf, it will be sent up to the console window of the debugger. And this again in the can be enabled if you're doing bare metal code. There are functions to enable it, or here in the operating system, we'll come on to this next week. We can see the event recorder, and then we can initialize it and start recording when we start the operating system. And the Kyle middleware and the operating system are instrumented. So here we have a separate event recorder window. And as all of the components execute, they can output these event annotations. So as our code executes, we get a very deep view into everything that the operating system's doing. And again, a number of filters so we can narrow down to find out what we're looking for. And this is the same for TCP/IP, USB, file system, etc. You can create these annotations for yourself. So there's a number of these effectively macro functions. So here we have the event recorder, we nominate the ID, and then we can output variables as well. So we can make those appear in the event recorder window. And we can extend our component viewer, so we can annotate these events in our XML file. And here we can take the ID and we can give it an informational name to start, stop. And we can also expand out different printf values as well. So we can convert from these raw numbers to an actual meaningful label. So here, as we use these event recorder labels and we annotate them, the XML will replace the raw numbers with these meaningful annotations. And again, this takes a little bit of effort to do, but once you've done it, it becomes incredibly useful over the lifetime of the project. Similarly, these event annotations can be used for performance analysis as well. So we can put a start and stop event at points in our code, so the entry and exit of a function, and then as they execute, we'll get the max min runtime between them, and average runtime. So we can start to build up some statistics in here about how our code's running. And again, this is still only using the low-cost debug adapters. Again, we'll come back to this in the operating system, but here we've got a couple of error checking tick boxes, so stack overrun checking and also usage watermark. So in our component viewer in the debugger, this will allow us to see the maximum amount of memory that a particular operating system thread has used. And if it uses too much memory, then the debugger will be halted on an overflow trap. All of this information can be displayed graphically in a new window within the debugger called the System Analyzer. So in here, we can look at variables and then we can chart them graphically. We have a trace of all our operating system threads. So as they execute, we can see how our execution is moving between threads. And similarly with our interrupts as well. So we can see the entry and execution time of all of our interrupts. With the Ulink Plus, we can also see current and voltage on the target as well. And here we have the event recorder. So all of the event messages that we're putting out are recorded in here as well. So again, you can expand this out and we can get very accurate timings by looking at any of these values as well. So we have cursors that we can set and measure time between events. So this gives you a very good view of how the code is executing on your device. As I mentioned with the Ulink Plus, as well as having the debug connector, it has a power monitoring connector in here as well. And this allows us to connect to power rails that are on the CPU. And sorry, beg your pardon. Oops, lost you. Got lost now. Sorry, pardon me. Oh, my mouse went out. Hang on. Yeah, so we can connect to the power rails, and then we have a sample rate of 20 megahertz, and this is two 16-bit Sigma Delta converters, and this will go down to about a resolution of 200 nanoamps and has a maximum input current of 2.5 millivolts. So the range is controlled by external shunts, so we can plug different shunts in here and get different current range. and the whole thing is opto-isolated up to about 1 kilovolts. So here on a real target, we're basically breaking into the power rail, connecting that via a shunt to the U-Link Plus, and then the green wire is connecting to Earth. So it's very easy to set up. There's no polarity to worry about on here, so you can swap those round. You'll just get a minus value instead of a plus value. So then in our event statistics, as well as getting timing, we can see current consumption between different events as well. So you can narrow down to different areas of code and see how much current that consumes over time. The U-Link Plus also provides a logic analyzer. So there are a number of 10 digital channels, and 2 of those can be converted into analog channels as well. Okay, so we can output analog voltages and get input analog voltages as well. And again, those can all be displayed within the system analyzer. There's an underlying scripting language, so we can talk to the various commands within the debugger, but those have been extended so that we can control the digital analog I/O as well. So we can read values, but we can also generate patterns down onto the hardware as well to do in-the-loop hardware testing. Another thing that a debugger is increasingly required to do is multi-core debug. So there are a number of microcontrollers that now have 2 Cortex processors within them. So one of the first of these, and one of the leaders in this area, is NXP. And probably quite a few years ago now, they brought out the LPC 4357. So this had a Cortex-M4 and also a Cortex-M0 on board the same chip. So both of these were free running processors, and they're linked together by a couple of interrupt channels so that they could signal each other. They were connected to the flash and RAM, but that flash and RAM was completely linear, so it was up to the developer to partition it between the M4 and the M0. Okay. And if both processors access the same memory location, you would get a bus fault. So it was a fairly minimal way of implementing both processors. And there have been a few innovations, but I think generally the way that dual core is done on a Cortex-M microcontroller is pretty much along these lines. So when we develop a project for a dual core application, we have 2 different microvision projects, one for the M4, one for the Cortex-M0 or M0 Plus, and we build those separately and we link them in place to where we want their code to execute. And then through the debug unit, we can connect both instances of microvision to the one debug adapter, and we can then control both cores from our 2 instances of our debugger. But we have a bit of a problem in this that gets a little bit fiddly, is that generally the M4 processor or core 0 will be executing from the reset vector from power on, but the secondary processor will be held in reset until it's released by the primary processor. Okay. So that means our M0 project can't communicate to the M0 on its own. We have to have a little bit of a framework in the primary processor to set things up, the bus structure, the clock tree, etc., and then release the M0. It also means when we want to do flash programming, this one can't talk to its processor to program the flash because it's held in reset. So we have to program everything via the M4. Okay. So here within the M0 project, when we build and link the code, there is a utility which is normally used to create a hex file, but here we can use this with a switch called CAD combined, and we can create a C image file, and inside here is a C array which has all the bytecode for our M0 executable code. So the executable isn't made into a binary or a hex file, it's made into a C array, and we then link that file into our M4 project, and we can locate that at the position we want to in the flash memory. So now when we download the M4 project, we're effectively putting in the M4 code, but we're also programming the M0 image as well. Okay, so this is a way to get an easy way to get the code on the chip without a lot of mucking around. When we start this debugger, we can then load the image set of the M0 code, so we still get a high-level debugging, and then we can just carry on as normal. So it's a bit fiddly, but it is achievable, and we've done a couple of projects with multi-core processors. So in terms of our Ulinks, we have a number, the Ulink 2, Ulink ME, which is a low-cost one that was sold with evaluation kits, Ulink Pro, and the Kyle tools also support a lot of the Sega tools and Sega JTrace as well. So I hope that's been useful today. Next week, we're going to look at using a real-time operating system. So if you haven't used an RTOS, this is a good introduction to get you going. And I would say it is worth investing the time in experimenting with an RTOS. Once you get familiar with it, it provides you a development framework that you get very used to, that helps you build reusable code, easily to maintain code. And once you've invested the time to learn about it, you really won't want to go back to using pure bare metal code.